All right. Rate law. Experimental methods. All right, so represent experimental data with a consistent rate law expression. So consistent rate means that we just take like the average of the rate over the whole reaction, as opposed to an instantaneous rate. Cool? Yeah. And I know you're gonna like go on the, what about calculus? I understand that, Oliver. Okay? I understand that you want to talk about calculus, okay? We'll get there. But for now, well, we may not get there actually, because this is algebra-based AP chemistry. Oliver back there, you should. Well, what is that? What is that word? There's a word for what you just did. Like scoff, but it wasn't a scoff. It was like a tongue click. Okay. Experimental methods can be used to monitor the amounts of reactants and products in reaction, determine the rate of the reaction. Yeah. Okay. Pretty straightforward. The rate law expresses the rate of reaction as proportional to the concentration of each reactant raised to a power. What? The rate law expresses the rate of a reaction as proportional to the concentration of each reactant raised to a power. To a power. Each one is raised to a power. So for instance, like pH, right? Yeah. Right? pH is the same way. Yeah. Right? So what is this rate law? What we're learning about right now. The rate law is so we'll look at the actual law itself in just a second. Okay. So we'll come back to that in just a second. Look at this. Just the power of each reactant. Pay attention. The power of each reactant in the rate law is the order of the reaction with respect to that reactant. The sum of the powers of the reactant concentrations in the rate law is the overall order of the reaction. Do we see how that works?
So what does the order do?
Yeah. What?
What does the order do?
Well, the order as like the overall order, meaning like what's the word that I'm looking for here? Help me out. Help me out, guys. No?
Kingdom. Class.
There's a word about the instead of order. It's like
Hierarchy.
Hierarchy.
I think that's the word you're looking for.
Yeah. Okay. So like what? Ah. Okay. So let me think here. So the order of the reaction with respect to one or more reactants. So it's like so look. So let me find something that'll help explain this a little bit better. So let's look at this. So this is, again, we have a reaction of nitrogen dioxide with carbon monoxide. experimental rate law. So rate, okay, of this here, the second order reaction, second order in nitrogen dioxide, zero order, zeroth, I don't know.
I don't even know what order it is.
So do you see this?
Yeah.
That it's to that power, that it's the second power. From the experiment, we see that it happens to the second power. It's an exponential curve, right? That's the order.
Okay,
Does that make sense?
sure. What is the case in?
The K is the no, it's not potassium. That is the K in this equation is like the it's not the reaction rate, it's K in algebraic notation represents the relation, right? So it's K, this is a direct relationship to the concentration of NO2 to the second power. Make sense? So if it was an inverse, it'd be like K over.
So what is
K?
The K is in algebra. K is a representation of a relationship.
well relationship between NO2 to the second and what?
This is the rate. That when you have the concentration. Okay. So
it's saying that the rate is proportional to or relational to NO2 to the second.
yes. So
Okay.
Through what relation?
what do you mean?
That is the
What
relation.
is K? Is K 9.3? Is K 2.7?
No, K is
The higher the K, the higher the this will be, right? Because you multiply them. Yeah.
Yeah. So how do you know what K is?
So see your order with respect to A, N, M, P, reaction order, or determining. Wait, is that? That's it. That's it. Got to find something.
So what do the orders have to do with all of this? Are they just exponents? That's it?
Yes.
They're just
But
exponents for
how does knowing the order help us?
How does it help us?
Yeah.
It helps us to understand the rate at which this type of reaction occurs.
So how do you find out the order? How do you find out what the K is?
So it has to be through experimental data that you get the order.
Okay.
So
What about
this
K?
isn't like going to be on the test or anything.
No, it'll give you it will give you some experimental data. John.
So how do we determine K from experimental data?
So let's look at let's see here. This is so this is 5.2 B3. Let's see if there's some practice problems on this. 5.2. Wait.
You say you weren't doing it.
What? This is obnoxious. What is happening? It's going through all these. Oh, there we go. 5.2. Okay, rate law. Here we go. Okay. So let's look at this. The initial rates of the reaction, represented by the equation shown above, blah, blah. Concentrations based on the data given in the table above, which of the following rate law expression for the reaction and why? What? Scroll up.
Oh, never mind.
So let's look at this here. So we have the concentrations. Yeah. So in this experiment, we have these two concentrations, so 0.0250 and 0.0510.
Why do they have to do 510 and not just 0.05?
I know, right? Why?
Why can't it just be a nice?
Why can't be it? Why can't it be just a
We
nice?
know how detailed that observation is.
No, yeah, I know. No, he's
Why
not.
can't
He's
the next one just be particle?
he's wanting it to be a more convenient number. That's all.
What?
Like this, right? This is a more convenient number. Does this make you happier, Elijah?
But then the number next to it is.
Okay, so let's look here. Okay. Initial rate of NOCl formation in the unit of moles per second, or moles second to the negative first, which is so obnoxious. Okay. So, based on the data given in the table above, which of the following is the rate law expression of the reaction and why? So which one of these is happening the fastest? Which experiment has the fastest reaction rate?
Probably experiment 2.
Okay, so we have conflicting answers here, 3 and 2.
So,
Yeah, Oliver? 3?
yeah. I think it's
Think it's 3? Are we in agreement? Is it 3? This looks like the biggest, yeah? But it is not, because it's to the negative fourth, right? As opposed to these two, which are the negative fifth. So this is the fastest one, right? This is the fastest one. So based on the data given in the table below, which of the following is the rate law expression of the reaction? Rate of KNO3, NO to the second power. Based on the initial rate quadrupled when NO was doubled, but remained constant when CL2 was doubled.
looking at the numbers on the table.
No, you're good. Does A make sense? So the initial rate quadrupled when nitrogen monoxide was doubled. So nitrogen monoxide was doubled, so we got a faster rate. Well, 4.55 times 10 to the negative fifth. What's 4.55 times 10 to the negative fifth times 4?
I don't know, you already calculated.
No, it said quadrupled. We're checking to see if it quadrupled or not.
4 times 4 is 16. 1.8 is a little bit more than 16. 4.5 is a little bit more.
Right, so it did quadruple. About.
4.5 squared. Now it'd be kind of close to your answer.
Yeah. When the initial rate quadrupled, so do you see how that works? As we increase this, because of the square, we increase the rate, right? We increase the rate by, if we make this 2 times, we increase the rate by 4 times, right? Does that make sense?
NO is the concentration.
Yeah. When it's in the brackets here, that's concentration. It's the amount in moles.
Well, the concentration, how can the concentration go up? Oh, is there like a third unlisted element? Is this in like an argon gas room or something?
What?
Well, the concentration of Cl2 didn't change at all. So clearly the concentration somewhere has to go down. The concentration somewhere else.
Well, but this is the reaction though.
Yeah.
We're looking at the initial rate of NOCl, the NOCl formation.
Yeah, and if there's a room filled only with NO and Cl,
Yeah.
then if the concentration of one went up, the concentration of the other would have to go down. Meaning that this must be a room with like binary gas.
No, because gases are compressible. You can have a higher pressure.
Well, yeah, but that would also mess with it, though, right?
Yeah, I
If
mean,
you increase the pressure, that could also make the speed faster, which,
that is true, but that's the whole nature of something being squared. Right?
what?
That you increase the concentration and therefore the reaction happens faster because you're increasing the pressure and the concentration essentially.
So you're saying that this doesn't work if you're not also increasing the pressure?
No.
Well, then shouldn't we assume that we're not increasing the pressure?
Well, maybe this is in a balloon, and so the volume changes, not the
So
pressure.
this holds true even if you're messing with multiple variables.
Yes.
Yeah.
Mhm.
So I can change all sorts of stuff, and then it's still proportional to NO squared.
And according to this data, it is.
Okay. So, so this data.
We are just looking at the reaction rate of this data.
So we didn't know beforehand that it was going to be proportional to its squared. That's what we had.
Right, that's what we're trying to figure out.
I see.
Okay?
Okay.
So is the rate proportional to the square of NO2?
Yeah.
So it's either A or D, right? Why would it be? Well, let me read.
So let's see here. Does the reaction rate go up when we increase the amount of Cl2? Oh, it goes up. Look. So let's compare experiment 1 and experiment 2.
Yeah, the reaction rate went up when we doubled the CO2. It just went up more when we doubled it.
Right. So look, you see this? As we increase the Cl2, it does go up, right? Right? It does go up, but it goes up more when we increase the NO2. Therefore, it is squared, the proportion, the K proportion, is NO2 squared Cl2 by itself. As this goes up, rate goes up. As this goes up, rate goes up by the square. So it should be D.
So how do we know that Cl and NO2 have
Wait.
proportionalities then? Shouldn't Cl have its own proportionality? Or does it?
See, according to this data, the proportion, the rate goes up as we increase Cl2, but it only goes up by a direct proportion.
No, what I'm saying is, if we divide experiment 3, the rate by 4, then will both of them have gone up by the same proportion, meaning K, right? Like, because the Cl doesn't have its own K. So that means that the K has to be the same for both of them. Can we show that?
So
That-
yeah, I mean, kind of. I mean, if I'm understanding you correctly, but let's just figure this question out really quick, okay? Because we're almost done with class. So is it C or is it D? Because oh yeah, because the squares on the NO2 are on the NO, right? So it should be D. We are all in agreement. We're figuring it out a little bit at a time. Congratulations, it's D. Yeah? Does that make sense? So again, don't worry so much about the K. It's just telling you like this is relational to this, right? And the things in the brackets are the concentration of that certain molecule. Okay? All right. You need a nap? Is your brain working too hard? All right. Make sure to like and subscribe.